In this video, we'll be talking about the bias-variance trade-off. When we fit models, one of our biggest challenges is trying to decide the complexity of the model. We have already discussed how an overly complex model can lead to overfitting, meaning we model some of the natural error in the data. These models typically perform badly when applied to new data that wasn't used to fit the model. But we also know that an oversimplified model won't actually capture the true form of the relationship. We further expand these ideas in the discussion of the bias-variance trade-off. Let's start with a simple example. In the images here, the black line shows the true model. The lines in color show models fit to different samples of data. In the image on the left, we see that the model is fairly consistent from sample to sample, but it is very bad at approximating the truth. In the image on the right, the lines are better at approximating the truth, but show a lot of variation from sample to sample. In order to thoroughly discuss the bias-variance trade-off, we need to use some mathematical notation. Each response, yi, can be written as a function of x evaluated at xi plus some error. This function f is what we call the true model. We then use samples of data to estimate the value of f at xi. The estimated functions based on our sample of data are called f hat of xi, and they will vary depending on the particular sample we take. The expected test MSE, that is the expected squared difference between the actual yi's and the value of the estimated model at a value xi, can be broken into reducible error and irreducible error. The irreducible error is sigma squared, the variance of the epsilon i's and the natural variation of the data around the true model. The reducible error is the expected squared difference between the value of the true model and the value of the estimated model for a value xi. Working through the math, of which I omit most of the details, this reducible error can be decomposed into the variance of f hat of xi and the square of the bias of f hat of xi. The variance of f hat of xi measures how much the estimated model varies from sample to sample. The bias of f hat of xi measures how far off the estimated model is, on average, from the true model. Ideally, we would like our models to have both low variance and low bias. But we will find it is often a balancing act. Typically, models that are too simple have higher bias but are less variable. More complexity or flexibility will typically decrease bias but add variance. We will use simulations to help illustrate this. For these simulations, the true model is y equals 4 plus 5x minus 0.5 times x squared plus epsilon, where epsilon is from a normal distribution with mean 0 and variance 16. The plot shows the true model in black. For a sample of 100 y's generated from the true model, 3 models were fit: an intercept-only model shown in purple, a quadratic model shown in orange, and a 10th order polynomial model shown in green. In the next few slides, we will evaluate the bias and variance of these models. Here we have taken samples of size 100, 200 times from the true model. Each of the 3 models was fit to each of the 200 samples of data, so each graph shows 200 models. In the first graph, where only an intercept was fit, we can see that this model is biased. It does not do a good job at all of approximating the true model. But we also see that it has low variation, with all the lines being very close together. The second graph shows the quadratic fits. They appear to show both low variation and low bias. This is what we would hope, since this is the true relationship. The third graph shows fits of the 10th order polynomial model. In general, the bias is still fairly low, but the variance is much higher than the other two. This shows the same models as the previous slide, but animates each model so you get a better sense of the individual variation from sample to sample. Here we dig in deeper to a specific value of x equals 5. The histograms show the distribution of the f hat of 5, that is, the estimated function evaluated at x equals 5. Taking the variance of these values gives the variance of f hat of 5, the variance of the estimated function evaluated at 5. The vertical black line shows the value of the true function at 5, f of 5, which is 16.5. The blue vertical line shows the average of the estimated functions at 5. The difference between these two lines is the estimated bias. We can also see the bias and variance estimates in the table. As expected, the largest bias occurs in the oversimplified intercept-only model. That model also has the smallest variance, and the overfit 10th order polynomial model has the largest variance. The quadratic model, which is the true model, has the smallest irreducible error, bias squared plus variance. We will continue to explore the bias-variance trade-off throughout the semester, oftentimes through simulations. For those of you looking for a challenge, especially if you have taken probability, I would encourage you to try to prove some of the mathematical detail that we skip.